Morning, students. Today we will start with the characteristics of digital ICs. So, characteristics of digital ICs, I will note down few characteristics, then we will start one by one. First one is propagation delay. First one is propagation delay. Propagation delay is denoted by TPD. Okay, second one is power dissipation. Power dissipation. Third one is figure of merit. Is denoted by FOM. Then you have fan out. After that, you have voltage and current parameters, voltage and current parameters. Then you have noise immunity. Noise immunity. After that, you have power supply requirements. Then you have last one, that's operating temperature. So these are the characteristics of digital ICs. So we will start with the propagation delay. Okay. Hello.
Yes, sir.
Okay, so we will start with the propagation delay. So first characteristics of this is propagation delay. Okay. So we have propagation delay. First characteristics is propagation delay. Before defining the propagation delay, I will make the figure for the same. So figure, which I will write this jot down, it shows the propagation delay for an inverter. So first of all, I will make the diagram for inverter, then I will show what is by definition. We will also get to know about the propagation delay. Before that, I will make the figure for the same. So this is inverter, first of all, inverter. Okay, so this will be A, and this will be your A bar, it's your inverter. So the figure below shows the propagation delays for an inverter. So I will jot down the figure. So this is the input. If this is considered as 0, then this middle one will be 50% of the input. This is final 100% of the input. So this is input 1, right? And this is the time duration. Horizontal axis is showing the time duration, and its vertical axis, it will showing its amplitude value. Now, since this is the input to the inverter, how you will get the output? That output will be obviously the inversion of that very thing which I have drawn here. So inverted, you just try to make the inverted of this. So this is 0, you will get the 1. How? I will show here this. Okay. This and here. So this is your 50%. This your input 1. Again, output of this input 1, right? And this one will be considered as 0. This is your 0. Okay, so this gap between these two, how much time it has taken to go from 1 to 0, this very time is called as TPHL, time taken by the output to go from 1 to 0 is called as time period. Propagation delay in going from high to low, that's denoted by TPHL. Similarly, how much time it took to go from 0 to 1, it is denoted by TPLH. How much time it took to go from low to high, that's denoted by TPHL. And this thing we are talking for the inverter. So you have input here, and then you get output for the inverter, because inverter, whatever you give, it will invert it. Suppose 1, it will be 0, high, it will give you the low. Same is the case with the figure. This figure will be inverted input, and you will get the resultant like this. But it will inversion, there will be certain delay in going from high to low and in going from low to high. So these are denoted by TPHL and TPLH. Now, what's TPHL? I will write down also this. Wait a minute. So we have TPHL. This is delay time. This is nothing but delay time in going from low, that's logic 0, to high, logic 1. That's delay time in going from low to high, right? Similarly, we have TPLH. Sorry, this is LH, and this is low to high. This is LH. Sorry, this is LH, and this is HL. So this is nothing but delay time in going from high to low. In going from high to low, high level to low level. Right? Now, one point you have to remember, that delay times are measured between the 50% points on the input and output transitions. they're always measured with respect to 50% of the value of amplitude. That means you will define this properly like this: the delay times are always measured between the 50% points on the input and output transitions, and its value will be always in nanoseconds, because delay time is very, very small. Its value will be always in nanoseconds, right? So it's measured in nanoseconds. We'll say that it's measured in nanoseconds, right? So finally, the propagation delay will be equal to TPD. It will be always equal to TPHL plus TPLH divided by 2. That means time delay in going from high to low plus time delay in going from low to high divided by 2, right? So I will note down certain BJT. In BJT, that means bipolar junction transistor. In BJT, TPLH will be always greater than TPHL. Why? Because due to a reverse recovery time. Due to reverse recovery time, right? Similarly, in fact, we have TPL, TPLH less than TPHL. That means TPHL is greater compared to TPLH. Why? Due to large capacitance form. Because due to large capacitance. It's because due to large capacitance form. To the large capacitance form. Right. So this is all about the propagation delay. Similarly, we will start with the second characteristics of this, that is power dissipation. So second one is power dissipation. So power dissipation is the amount of power dissipated in an IC. So it's an amount of power. It is the amount of power dissipated in an IC. So it's determined by the current ICC, which draws from VCC supply. So there will be some supply that's called VCC, then current drawn from the supply is VCC. So it's determined by the current ICC drawn from the VCC, right? Okay, so in general, ICC will be equal to ICCH plus ICCL divided by 2. So ICCH is current value when all inputs are high, and ICCL means is the current value drawn from the supply VCC when all the inputs are low. So you will say that, note down, okay, this. So this is current value when all inputs are high. Similarly, this is current value when all inputs are low. Low. Okay. So power dissipation, that means power dissipation average, will be then equal to ICC into VCC. This is supply voltage. Okay, and its unit is always in milliwatts. It's measured in milliwatts, measured in milliwatts. Okay, so the third characteristics is figure of merit. So third one is figure of merit, FOM. FOM is mathematically equal to product of propagation delay into power dissipation. So it's mathematically equal to product of propagation delay and power dissipation. So it's specified in picojoules. Joules. It's specified in picojoules. Since FOM is nothing, if you can calculate its unit, FOM is equal to product of propagation delay. Propagation delay is always denoted in nanoseconds. So there will be power dissipation. It's denoted in milliwatts. So watt and second, it will give the energy value. Wait a minute. So it's it's denoted, so it's a product of nanosecond into milliwatts. What you will get picojoules, nano into milli, and 10 raised power 9, 10 raised power minus 3, that 10 raised power 12. So you will get pico, and watt into second, you will get joules. So you will get the unit as energy unit, so picojoules. So there is certain constraint which we will put on these things. Suppose TPD will increase and power dissipation will decrease, so FOM remains constant. It will remain constant also in this case when TPD will decrease and power dissipation will increase. So in both cases, it will remain constant. So for the best operation of ICs, FOM should be smaller. Why? It should be as much small as possible. Reason, because you need that power dissipation should be as minimum as possible. Similarly, propagation delay should be also minimum. There should be minimum delay while you are getting the output. That means there should be minimum delay while processing any input. Got it? So ultimately you will write down last that FOM should be minimum. FOM, it should be minimum. Minimum. It will remain constant. FOM will remain constant. It will be constant in these two scenarios when TPD will increase and power dissipation PD will decrease, or when TPD will decrease and power dissipation average will increase. In both cases, it will remain constant and its value should be minimum. So these are the three most important characteristics of digital IC. Hope you people have understood. And tomorrow we will continue with the characteristics of digital ICs.